Hello and welcome to this revision session for AQA A-Level Physics, Paper 2 on the topic of capacitance. So if we've been successful and we've learnt in today's lesson, we should be able to answer A-Level Physics examination style questions, assess our understanding on A-Level Physics and understand what topics we need to improve upon for A-Level Physics. So how should you prepare for this revision session? When you complete your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and in this left hand side section write down your working out and answers to the questions in the revision session. When you're doing this, make sure to write in full sentences and show the full working out. Whilst in the right hand side, write down any bits of information which you find useful, any hints and tips on answering questions from this revision session. At the end of the revision session, write up these notes into a revision sheet for you to use independently. So how should you be revising for A-Level Physics? The first step is to learn the key facts, so use things like revision guides, class workbooks, student prep notes and the textbooks to learn the key ideas of the course. You may wish to write out mind maps or notes yourself. Next, test yourself. Use Caboodle, Seneca, the student knowledge checker to quickly test your own knowledge, and you may wish to do this from your own cue cards. Then finally, practice exam style questions. So use exam prep books, homework books, supervised study books, additional workbooks to answer examination questions and mark your own work. And you may wish to download your own past papers to do this. So you should be learning the key facts, testing yourself, and then practicing exam style questions. So what are the key facts to do with capacitance? Well, capacitance has the definition of capacitance to be the charge over the potential difference. Now the capacitance of a parallel plate capacitor is equal to the area of the plates times by the permittivity of free space times by the relative permittivity of the dielectric constant divided by the separation of the two plates. Now there is dielectric action that takes place in a parallel plate capacitor. So the dielectric contains polar molecules which align in an electric field, reducing the field strength and increasing the capacitance of the capacitor. Now we can actually work out our energy stored in a capacitor with the equation E is equal to a half times by QV, or a half times by CV squared, or a half times by Q squared over C, and this can be derived from the area under a QV graph. Now we can also look at capacitance charge and discharge, where you know that for graphs of charge, voltage or current against time, for charging shows an exponential increase and for discharging shows an exponential decay. Now it's also important to note that the time constant is the time it takes for a value to change significantly, where it tends to drop to 37% of its initial value. Now the time taken to half is equal to 0.69 times by the time constant. Now our key equations for discharge are Q equals Q0 e to the power minus t over RC, and for charging Q equals Q0 times by 1 minus e to the power minus t over RC. So with that, let's have a look at some general check questions to do with capacitance. So the first question says, what is happening for a capacitor plate to become negatively charged? Pause the video now, then unpause the video when you want to go through your answer. Well, a capacitor plate will become negatively charged when electrons are flowing through the circuit and being deposited onto the negatively charged plate. So why do electrons move onto the negatively charged plate? Well, the electrons are repelled by the negative charge found at the terminal of the power supply. What is happening for a capacitor plate to become positively charged? The electrons are flowing off that plate and not being replenished as the current flows. Why do electrons leave the positively charged plate? Electrons on the positively charged plate are attracted to the positive terminal of the power supply. Why does the charge of a capacitor generate a uniform electrical field in the capacitor? As the charging process causes a potential difference to be formed over the two plates. Why does the current start to fall in the circuit as the capacitor is charging? As the capacitor is charging, it reduces the flow of charge around the circuit. Why does charging a capacitor not immediately reduce the current to zero? As the electrons must flow around the circuit to reach the positively charged plate, this takes a long time as the charge flows slowly throughout the circuit. How could the capacitance of a capacitor be increased? The plates could be moved closer together. There could be a stronger insulator placed between the plates, or the plates could be larger. How could the rate of charge in a capacitor be increased? The rate of charging could be increased by having a larger charge flowing or by decreasing the resistance of the circuit. How could a capacitor fail when charging? If the insulator between the two plates breaks down and the charge can flow between the two plates, as this will complete the circuit. Why does the rate of charge decrease as a capacitor charges? As there is already charge on the plates, adding further charge of the same type is repulsive, so it's harder to do, so it takes longer to complete. What is the current flow when the capacitor is fully charged, and why? The current flow is zero, as the capacitor is now fully charged, so there's no flow of charge around the circuit anymore. What happens to the capacitance of a capacitor if the area of the capacitor plate has increased, and why? The capacitance of the capacitor increases as more charge can be stored on the plates, as the charge will spread out evenly. Why does the charge on a capacitor plate spread out evenly? As the charge is all negative or positive, they will repel each other, causing the charge to spread evenly. What happens to the capacitance of the capacitor if the distance between the two plates is increased, and why? The capacitance has decreased. This is because the electrical field strength has decreased, V over D, so there's less of attraction between the two plates, so less charge can be stored. Why is a dielectric needed for a capacitor to work? The dielectric material prevents the charge moving between the plates of the capacitor. This allows the charge to be stored. Suggest why many capacitors are constructed as below. This arrangement is two metal plates wrapped up and separated by a dielectric. This increases the surface area of the plates and decreases the separation of the plates. Both of these factors increase the capacitance. What is a polar molecule? A polar molecule is a molecule with areas of positive and negative charge due to an uneven distribution of electrons in the molecule. What is the orientation of polar molecules when the capacitor is uncharged? Why? The orientation of the polar molecules is random, as there's no electrical field influencing the molecules, as there's no potential difference between the plates, as it's not charged. What is the orientation of the polar molecules when the capacitor is charged, and why? The orientation of the polar molecules is anti-parallel to the electrical field generated by the capacitor, as the charged objects are influenced by the electrical field. Why do polar molecules align anti-parallel to the electrical field generated by the capacitor? Opposite charges and like charges will repel, so therefore the molecule orientates themselves in the opposite direction to the electrical field generated. So the negative will go to the positive and the positive will go towards the negative. What happens to the electrical field strength produced by the capacitor with polarized molecules in the dielectric, and why? The electrical field strength decreases, as the electrical field strength is a vector and the two field strengths are acting in opposite directions. What happens to the amount of charge stored by the capacitor plate with polarized molecules in the dielectric, and why? The amount of charge stored on each capacitor plate increases as the repulsion on each plate of adding more charge is lessened by the opposite charge of the polar molecules attracting the charge to the plate. What happens to the capacitance of a capacitor with polarized molecules in the dielectric, and why? The capacitor can store more charge on each plate for each 1 volt as it has across the plates, so therefore the capacitance can increase. Does work have to be done to a capacitor to remove a polarized dielectric from the capacitor, and why? Work must be done to remove a polarized dielectric from the capacitor, as the polarized molecules are attracted to each plate, so work must be done to overcome this attraction. How can a capacitor be discharged? Why is this? A capacitor is discharged when the power supply is removed from the circuit. This is because the power supply is no longer there to maintain the charge imbalance on the plates, so the charge will flow off the plates. Why can the discharging process be considered an example of exponential decay? It is an exponential decay as the rate of decrease is decreasing exponentially with respect to time. Why is work done into a capacitor when it is charging? Work is put into the capacitor to force the charge onto the plates as it experiences repulsion from the existing charge already on the plates. What is the relationship between charge stored and the work done on the capacitor, and why? Work is put into the capacitor and the charge stored squared onto the plates are directly proportional, because the greater the charge onto the plates, the greater the repulsive force exerted on the charge, so the work done is greater. What is the energy store in a capacitor? The capacitor is storing electrical potential energy when it is charged. Where is the energy stored in the capacitor? The energy is stored by the capacitor in both the charged particles, in the charge on the plates, and in the dielectric, because they're a charged particle in an electrical field. Capacitors tend to have a low energy stored but a high power output. Why is this? The capacitor can discharge the small quantity of energy it has stored quickly, so the time of discharge is low, giving a high power output. Let's now have a look at some examination style questions to do with capacitance. So, a research lab is developing a high-speed switching circuit. To reduce delays, the circuit stores energy in a parallel plate capacitor. The capacitor has square plates of side length 12 cm separated by a dielectric of thickness 1.50 mm and a relative permittivity of 4.8. The capacitor is charged to a potential difference of 60 volts and then discharged quickly through a resistor. Calculate the capacitance of the capacitor. Determine the total energy stored in the capacitor as 60 volts and hence calculate the maximum charge stored. The research team proposes replacing the dielectric with a material of higher permittivity and reducing the separation to 1 mm, keeping the plate area the same. Consider how both changes would affect the stored energy for the same applied voltage and explain why those changes may be beneficial or risky for the circuit. So, pause the video now, then unpause the video when you want to go through your answer. Right, in our first question, we need to work out the area, which is the length squared because it's a square. So we work it through to be 0.0144 meters squared. We then know capacitance is area times by relative permittivity times by the permittivity of free space over the separation. Pop in all the values and we get 4.07 times 10 to the minus 10 farads. Next, we know E is equal to a half CV squared. So we pop in all the values there and we get 7.33 times 10 to the minus 7 joules. We know Q is equal to CV. So we can then pop all those values into the equation and we get 2.44 times 10 to the minus 8 coulombs. Now, increasing the relative permittivity will increase the capacitance. So therefore, this tells us that decreasing D will also increase the capacitance. Now, since E is equal to a half CV squared, increasing C will increase the energy stored. Now, a higher energy stored will lead to a faster switching and better performance in the circuit. However, you have to be careful, as if there's too much energy, it may cause our dielectric to break down or overheat, so we need to consider how strong we make our dielectric constant. A manufacturer is developing a regenerative braking system for an electric car. During braking, kinetic energy is stored temporarily in a bank of capacitors before being released into the drive system. Each capacitor has a capacitor of 2.50 farads and is charged to 30 volts. A dielectric material with a relative permittivity of 3.2 is used inside each unit. Determine the amount of charge stored in the capacitor when fully charged. During one braking event, the car's kinetic energy decreases by 90 kilojoules, which is captured by a bank of 100 identical capacitors. Determine whether this bank can store all of the energy from the braking and justify your answer. Now, the designers are considering increasing the relative permittivity of the dielectric while keeping voltage and geometry the same. Discuss how this change would affect the energy storage. So, pause the video now, then unpause the video when you want to go through your answer. Right, in this one, we know that energy is equal to a half CV squared. So you can work out what your energy would be by doing a half times by 2 times by 30 squares, 1,125 joules. We can then use this information, work it all through to get out our charge by saying Q equals CV. So 2.5 times by 30 is 75 coulombs. Now we know the total capacity is going to be 100 times by the energy we've previously calculated, because there's 100 of them, so it's 112,500 joules. Now the break-in energy is 90,000 joules, so the bank can store more than the required energy, so it will be able to do this. Now again, increasing the relative permittivity increases our value, since E equals a half CV squared. Increasing C will be from increasing E, so therefore, increasing the relative permittivity, so therefore it increases the energy stored. Now the higher energy storage could improve the system performance and the range, but the risk is more energy is more heat during the discharge. You need to think about how you cool your capacitor as it works, and also you've got the risk of breakdown in between the two plates if the dielectric strength is not sufficient. A paparazzi photographer uses a high-speed camera flash powered by a parallel plate capacitor. The capacitor consists of square plates of side 4 cm, separated by a dielectric of thickness 1.20 mm and a relative permittivity of 5. The capacitor is charged to a potential difference of 250 volts before discharging rapidly through the flash tube. Calculate the capacitance of the flash capacitor and determine how much energy it stores when charged to 250 volts. A new version of the camera uses a dielectric with a higher permittivity and thinner separation to reduce recharge time. Explain how both changes affect the performance of the flash system. The dielectric used is a polymer containing a simple polar molecule. Explain what is meant by a polar molecule and describe how these molecules behave when the electrical field strength is applied and then removed. So, pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, we know that the area is equal to L squared, as it's a square. So we get our area to be 1.6 times 10 to the minus 3 meters squared. We then use the parallel plate capacitor equation to work out our capacitance to be 5.9 times 10 to the minus 11 farads. We know energy is a half CV squared, so we pop that all in and we get 1.84 times 10 to the minus 6 joules. Now, a higher relative permittivity increases capacitance, so more charge will be stored for the same voltage. Now, a thinner separation increases the field strength, leading to faster charging and a higher energy storage. So this gives you a better flash brightness and recharge speed. However, remember that smaller separation could lead to an increased chance of the dielectric breaking down. Now, a polar molecule is a molecule with a permanent electrical dipole due to the uneven distribution of the electrons. In no field, the dipoles are randomly orientated, but in an applied field, the molecules align with the field, reducing the internal field. Now, when the field is removed, it is causes the molecules to return back to random alignment, so we'll lose energy via dissipation. To protect a sensitive data during sudden power loss, the right head of a hard drive is backed by a charge resistor discharge circuit. The capacitor stores energy while the computer is running and discharges when the power is lost, giving the hard drive enough time to save and park safely. A 4700 microfarad capacitor is used with the resistor of resistance 120 ohms. The capacitor is fully charged to 5 volts and discharged through the resistor as soon as power is lost. Calculate the time constant for the discharge circuit. Determine the time taken for the potential difference across the capacitor to fall to 2.5 volts. The graph below shows the voltage across the capacitor as it discharges from 5 volts. A student proposes a log linear plot to determine the time constant. Explain what should be plotted on each axis and how the gradient of the graph relates to the circuit components. Discuss how the design of this capacitor resistor system helps to protect data during a sudden power loss. In your answer, include both physical and practical considerations. So, pause the video now, then unpause the video when you want to go through your answer. We know that time constant is equal to RC, so it's 120 times by 4700 times by 10 to the minus 6, 0.564 seconds. Now, you'll have noticed in this next question that it is going to half the particular value. So as a result, we can use the equation that we use for the time taken to half, which is T is equal to 0.69 RC. So we do 0.69 times by 0.564, so we get 0.391 seconds. Now in our next question, how can you work out the graph correctly? Well, we will plot log v against t. So we can then say, well, log v is equal to log v0 minus t over rc from our equation. So therefore the gradient, when we use that as to y equals mx plus c, is equal to 1 over rc. So that tells us that the time constant is inverse of the gradient. Now finally, the discharge provides a brief power for the computer to complete the save. Now the time constant chosen is to match the time needed to finish a safe shutdown by the computer, and a large capacitance ensures that enough stored charge is present to allow this to take place. The next question says, an automatic sliding door in a secure facility uses a timing circuit involving a capacitor and resistor to delay opening. When a sensor is triggered, a 2200 microfarad capacitor begins to charge through a resistor of 1.8 kiloohms supplied by a constant voltage of 6 volts. The capacitor voltage controls a switch. When the voltage across the capacitor reaches 5 volts, the door begins to open. Calculate the time constant for this circuit. Determine the time taken for the capacitor to reach 5 volts. Then the security engineer wants the delay reduced by 30% without changing the supply voltage. Suggest and justify one practical change to the circuit that would achieve this, and explain how this change affects our charging curve. So, pause the video now. Then unpause the video when you want to go through your answer. Right, so when we answer this particular question, the first one is looking at our time constant. So our time constant is going to be equal to RC. So it's 1800 times by 2200 times 10 to the minus 6, 3.96 seconds. Now we want to use our charging equation. So we can then work it all through, pop in all the values, and then we work it through to be equal to 7.09 seconds. Finally, to get that 30% reduction, you would either reduce the resistance or the capacitance. This is justified as T equals RC, so either reducing R or C lowers this value of T. This means that our voltage reaches 5 volts faster and therefore our door opens sooner. Now on the graph, the curve will rise more steeply and reach 5 volts earlier, but follow the same general pattern. A student is investigating how changing the resistance in an RC circuit affects the discharge of a capacitor. Two capacitors of identical capacitance are charged to the same voltage and then discharged through different resistors. The graph below shows how the potential difference across each capacitor varies with time. Explain which capacitor is discharging through the greater resistance and justify your answer with reference to the graph. Now use the values from the graph to estimate the time constant T for curve A. Then the student suggests that the area under each curve represents the energy transfer during the discharge. Evaluate the suggestion and discuss how the area under two curves would compare. So pause the video now, then unpause the video when you want to go through your answer. Right, in our first one, what do we know? We can work everything through. So what we can see from the graph is that curve B discharges more slowly than curve A. The slower discharge implies a larger time constant because T equals RC. Now since C is constant, this tells us that B must have therefore the greater resistance. Now we also know that we can work out what our time is going to be for the time constant if we know that V has dropped to 37% of our V0. So from the graph we know it starts at 6, so it's 0.37 times 6, which is 2.22 volts. So then read from the graph that the time at that point is 2.8 seconds. Now finally, the area under a V against T curve does not directly give energy, but the area under an I against T or a VI over T curve would. Now since both capacitors would start with the same C and the same V, our total energy transferred is equal. However, curve B releases energy over a longer time, so it's the same area but spread out more. In recent years, supercapacitors have been developed. These components charge and discharge in a similar manner to standard capacitors, but can have capacitances of more than 10,000 farads. These can be used as backup supplies in many circumstances. A 120 farad supercapacitor has an internal resistance of 30 milliohms. At time t equals 0, it stores 300 joules. Calculate the minimum time taken for the capacitor to transfer 250 joules through discharging. Suggest why this is a minimum value. Pause the video now, then unpause the video when you want to go through your answer. Right, we know that the PD across the capacitor, okay, can be from when E equals 300 joules is going to be V is equal to the square root of 2E over C. We've rearranged our energy equation. So we pop in all the values and we get to be 2.24 volts. Now the PD across the capacitor when the energy is 50 joules, we work it through again with the same equation, is 0.91 volts. So therefore we can say the time is the negative log over this 0.91 over 2.24 times by 30 times 10 to the minus 3 times by 120. So therefore it's 3.2 seconds. Now this is a minimum value because there's no external load acting on the circuit. This question is about a charging capacitor in a circuit with two resistors in series. Show that the time constant of the circuit is about 15 seconds. Then the graph in figure 2.3 shows how the PD across the capacitor varies with up to 5 time constants. Add a line to the graph that shows how the PD across the 4.7 kilo ohm resistor varies with time. Add another line to show how the PD across the 2 kilo ohm resistor varies with time. Label the lines. Then calculate the time it takes from the start of the charging for the PD across the capacitor to reach 5 volts. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this answer, how do you work it through? So RC is equal to T is going to be equal to the time constants. We pop that through and it's 14.7 seconds. Now, next one, we know that it should at 4.7, 4 should be exponentially decreasing to 0 at 5 time constants, and then 2 kilo ohms at 2 or 1.8 volts at t equals 0, exponentially decreasing to 0 volts at 5 time constants. Now we know here that E minus T over RC is going to be equal to 1 minus 5 over 6 by looking through our equation, pop in all the values and work it through, and T is equal to 27 seconds. Our next question says a student investigates the charging of a capacitor. The student sets up the circuit as shown using a 47 microfarad capacitor. The capacitor is initially uncharged. The switch S is now closed. The laptop connected to an interface displays a graph of current against time as the capacitor charges. The variable voltage supply is set to 6 volts. Calculate the maximum charge stored by the capacitor. Suggest an alteration the student could make to the circuit to increase the maximum energy stored by the 57 microfarad capacitor. Then the use of analogies from everyday life can help improve the understanding of physics concepts. Vehicles used in a car park may be taken as an analogy for the charging of a capacitor. Use your knowledge of physics to comment on this analogy. So pause the video now, then unpause the video when you want to go through your answer. Right, what do we know in our first question? So what we can say is that C is equal to Q over V. We've got C, we've got V, so therefore we can work out Q. So therefore we work out Q, and that is going to be equal to 2.8 times 10 to the minus 4 coulombs. Now how could you increase the maximum energy stored? Without changing the capacitor, the easiest way is to increase the supply voltage, as E is equal to a half CV squared. Finally, how can you work out the next one? Well, think about the capacitor as the car park. A capacitor is likened to the car park, so just as a car park can store a certain number of cars, a capacitor can store a certain amount of electrical energy in the form of electrical charge. Think of the charge of the capacitor. When the car park is empty, it's akin to a discharged capacitor. As cars enter the car park, it represents the process of charging the capacitor. When a capacitor is connected to a voltage source, electrical charge accumulates on its plates, like cars filling up the parking lot. The voltage is like the parking spaces. The voltage across the capacitor can be likened to the number of parking spaces in the car park. A higher voltage means a greater potential difference and more parking spaces for the cars to accumulate. However, the issues are the dielectric material. Real capacitors often have a dielectric material between their plates, which affects their capacitance. This is not represented in the analogy. The discharge process. It doesn't cover the discharge process of a capacitor, where stored energy is released. There's no representation in our image of the cars leaving the parking lot. And then finally, electrical fields and potential energy. It doesn't delve into the idea of electrical fields and potential energy, which are fundamental concepts in understanding how the capacitor behaves. A student carries out an experiment investigating the charge of a capacitor using the circuit shown. Describe how the results of this experiment are obtained and used to show how the voltage across the capacitor varies with time when the capacitor is charging. The capacitor is initially uncharged. The variable voltage supply is set to 12 volts. Switch S is closed. The capacitor becomes fully charged. Calculate the maximum energy stored by the capacitor. then suggest an alteration the student could make to this circuit to increase the maximum energy stored by the 47 microfarad capacitor. So pause the video now, then unpause the video when you want to go through your answer. Right, so you would close the switch and then take readings on the voltmeter at regular time intervals. You would then plot a graph of voltage against time. We know E is equal to a half CV squared, so you pop in the values and E is equal to 3.4 times 10 to the minus 3 joules. Finally, we can't change the capacitance of the capacitor, so to increase the energy, we increase the supply voltage. The properties of the capacitor make them useful in timing circuits. The following circuit is used to provide an input Y to an integrated circuit. Initially the capacitor is uncharged, the switch S1 is closed. Sketch a graph to show how the potential at point Y varies with time. When the potential at Y is 8 volts, the switch S2 is closed. Calculate the time taken for the potential at Y to decrease to 2 volts. Calculate the energy stored on the capacitor when the potential at Y is 2 volts. Then when the potential at Y is 2 volts, switch S2 is open. Calculate the power dissipated by the resistance R1 when the potential at Y is 2 volts. So pause the video now, then unpause the video when you want to go through your answer. Right, so what you would draw is a line that's approximately an exponential curve starting at 0 and increasing in potential. It begins to flatten off at a maximum of 8 volts, and we use a time constant to work out about an increase when we're charging of the values. So you can see on here, this is a sketch of what it should look like. We then use our equation V equals V0 e to the minus t over RC. Pop in all the values, work it all through, and we get 5.61 milliseconds. We then know that the work done or energy stored is a half CV squared. So you do a half times by 1.5 times 10 to the minus 6 times by 2 squared, so the work done is 3 times 10 to the minus 6 joules. Finally, we know that I is equal to V over R, so you can work at 6 over 3.3 kilo ohms plus 2.7 kilo ohms is 1 milliamp. We know power is I squared R, so it's 1 milliamp squared times by 3,300, that equals 3.3 times 10 to the minus 3 watts. So that brings an end to our revision session today. So if we've been successful in our revision session, we should be able to answer A-Level Physics examination style questions, assess your understanding on A-Level Physics, and understand what topics we need to improve upon for A-Level Physics. Thank you so much for watching this revision session on the idea of capacitance, which is part of AQA A-Level Physics Paper 2. Thank you so much and have a lovely day. Hello and welcome to this revision session for AQA A-Level Physics Paper 2 on the topic of capacitance. So in this revision session we're going to look at how to answer examination questions on A-Level Physics Paper 2. So if we're successful and we learn in our revision session today, we should be able to answer A-Level Physics examination style questions for capacitance. You should have an understanding of what you know for A-Level Physics capacitance topic, and then understand what topics in the capacitance module you need to improve upon for AQA A-Level Physics. So how should you prepare for revising in this revision session? Well, when you complete your work in this revision session, divide your piece of paper into 2 sections. Make the section on the left hand side larger than the right hand side. In that left hand side section, write down any working out or answers to the questions in the revision session. When you're doing this, make sure you write in full sentences and show your full working out. Whilst in the right hand side section, write down any bits of information which you find useful or any hints and tips on answering questions from the revision session. At the end of the revision session, write up these notes into a revision sheet for you to use independently. Now, in terms of how you should revise for A-Level Physics, the first step you should be doing is learning the key facts. So use revision guides, class workbook, student prep notes and a textbook to learn the key ideas of the course. You may wish to make mind maps or to write out notes yourself. Secondly, test yourself. Use the Caboodle e-learning platform, Seneca, student knowledge checkers to quickly test your knowledge. You may wish to do this from cue cards. And then finally, practice with examination style questions. So use exam prep books, homework books, study books, additional workbooks to answer exam questions and mark your own work. And you may wish to download your own exam past papers to do this. So in terms of how you should be revising your A-Level Physics, there are 3 steps. Step 1, learn the key facts. Secondly, test yourself. And then thirdly, practice an examination style questions. Now, in terms of the questions we'll cover in this revision session, there'll be 3 types of question we'll look at. There'll be general general check questions, the basic questions designed to probe your understanding of the key concepts of the topic. Secondly, our checkpoint questions. These are more challenging questions designed to place your own knowledge and understanding of the topics into different applications and contexts. And finally, assessment points, past paper exam questions which mimic the type of questions found in public examinations. So with that being said, let's now have a look at some capacitance questions. The first question says, a 470 microfarad capacitor is connected across the terminals of a battery of EMF 9 volts. Calculate the charge on the plate of the capacitor. Secondly, calculate the potential difference across the terminals of a 2200 microfarad capacitor when it has a charge of 0.033 coulombs on its plates. And then finally, calculate the capacitance of a capacitor if it stores a charge of 2 coulombs when there is a potential difference of 5000 volts across its plates. So pause the video now, then unpause the video when you want to go through your answers. Right, so this is using that key equation that capacitance is equal to charge over potential difference. So if we have a look at this particular equation, we can rearrange it and we can make charge the subject. So we can say Q equals CV. We turn micro into farads, so it'll be times 10 to the minus 6. So we get 4.2 times 10 to the minus 3 coulombs. We rearrange this one to make V the subject. V is Q over C. Once again, we turn micro into the normal farads by times 10 to the minus 6, and we get 15 volts out. Then finally, we say capacitance is charge over potential difference, so we work it through and we get 4 times 10 to the minus 4, which is 400 microfarads. The next question says, a student inserts 2 bare copper wires into a lump of wet clay. The clay is dried out. The student suggests that he has made a capacitor. Explain whether this is correct. The next question says, the charge stored by a capacitor connected to a 12 volt battery is 2.4 times 10 to the minus 5 coulombs. Calculate its capacitance in farads and then microfarads. A capacitor stores a charge of 30 picocoulombs when the potential difference across is 3.2 volts. Calculate the charge stored in picocoulombs when the PD is increased to 8.7 volts. Then the capacitor of capacitance 200 microfarads is connected to a 10 volt supply. Calculate the number of electrons removed from the positive plate of the capacitor. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you've got to understand what the definition of a capacitor is. Yes, it is a capacitor because it consists of 2 metal electrodes separated by an insulator, which is what we define our capacitor to be. The next one, once again, we use the equation capacitance equals charge over potential difference, pop in the values, and we get 2 microfarads. In this next one, we then say, well, looking at the equation, if we've got a constant capacitance, we can say that Q is directly proportional to V. So when we work it through in the terms of ratios, we can say it's 81.6 picofarads. And then the last one here, what you can do is use Q equals CV, work it out to be 2 times 10 to the minus 3 coulombs. Remember, microfarads turns into farads by times 10 to the minus 6. We then work out how many electrons we've got by taking our overall charge, dividing by the charge of an electron, 1.6 times 10 to the minus 19 coulombs, and we get 1.3 times 10 to the 16 electrons. The next question says, a capacitor of capacitance 0.010 farads is connected to a 1.5 volt cell. Calculate the number of electrons delivered by the cell to the capacitor. Then an uncharged capacitor of capacitance 1500 microfarads is connected in a circuit. The current in the circuit has a constant value of 80 microamps. The capacitor is charged for a time of 60 seconds. Firstly, calculate the charge and the PD across the capacitor after a time of 60 seconds, and then sketch a graph of PD across the capacitor against the time over a period of 60 seconds. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, once again, Q equals CV, work it through, divided by the charge of an electron, 1.6 times 10 to the minus 19, we get 9.4 times 10 to the 16 electrons out. In this next one, we've got to use an equation from electricity. Charge is equal to current times by time. So when we turn micro into amps by times by 10 to the minus 6, so we work out our charge to be 4.8 times 10 to the minus 3 coulombs. We can then say V equals Q over C to get 3.2 volts. Now, if you look on here, how will the potential difference go against the time? Well, you'll notice that it'll be a straight line graph through the origin, and you'll get a value of V equals 3.2. It's 60 seconds because from the answer to our previous question. The next question says a 22 microfarad capacitor is charged by using a constant current of 2.5 microamps to a PD of 12 volts. Calculate the charge stored on the capacitor at 12 volts, the time taken. A capacitor is then charged by a constant current of 0.5 microamps to a PD of 5.0 volts in 55 seconds. Calculate firstly the charge stored and then secondly the capacitance of the capacitor. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one again we're using Q equals CV, so we will put them in. Remember, micro turns into the farads by times 10 to the minus 6, so we get 2.64 times 10 to the minus 4 coulombs. Again, we can say Q equals IT, so therefore T equals Q over I. We've already got Q from the question, okay, and we've got I from the question, so we can work it through. Remember, we worked out Q in our previous answer, so we can pop it through and we get 105.6 seconds. In this second question, once again, Q equals IT. So we know I, because we can work it through, be 0.5 times 10 to the minus 6, times by the time in seconds, 55, so you get 2.75 times 10 to the minus 5 coulombs. And then we can work out the capacitance by saying C equals Q over V. We worked out Q in our previous question. We know the value of V from the information given, it's 5, so you get 5.5 times 10 to the minus 6 farads. The next question says a capacitor is made from a plastic bin bag sandwiched between two sheets of aluminium foil 60 centimeters times by 30 centimeters in size. The bin bag is 0.080 millimeters thick. Plastic has a relative permittivity of 4.0. Calculate the capacitance of this capacitor. Then the capacitance of a parallel plate capacitor is 8 picofarad. State and explains capacitance when the separation between the plates is doubled, then the area of overlap between the plates is halved and their separation is also halved. Then a capacitor is made from two circular plates of diameter 20 centimeters. That are separated by an insulator. The insulator has a relative permittivity of 4.0 and a thickness of 1.2 millimeters. The capacitor is connected to a 6-volt battery. Calculate the maximum charge stored by the capacitor. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this one you've got to use the parallel plate capacitor equation. So that is C equals the area times by ER E0 over D, where ER is our relative permittivity and E0 is the permittivity of free space, which is a constant given to you on the equation sheet. You pop in all the values given to you in the question. Now remember, you have to turn centimeters into meters and you have to convert millimeters into meters as well. So you can pop those through as shown in the working out on the screen. Pop in our values and we get 80 nanofarads. The next one, you can see from the equation above that C is directly proportional to 1 over D. So therefore if D is doubled, well C will then half. So it's gone from 8 picofarads to 4 picofarads. Once again, we can see from the equation above that C is directly proportional to A, but C is directly proportional to 1 over D. Now, because A and D will both change by the same magnitude, the same factor, they'll cancel each other through, so we get 8 picofarads. This next question again, we're going to have to use our equation from above, the parallel plate capacitor equation, but this time we're going to have to work out our area. Now we can see that the area is going to be just for one of the plates, so we do pi r squared. Now we've got the diameter in centimeters, so we convert that to a radius, which is 10 centimeters, and then convert it into meters, so 0.10 meters, pop in all the values, work it through, and we get 9.2 times 10 to the minus 10 farads. We can then work out our charge stored by saying Q equals C times by V. We've just worked out the capacitance, we know the voltage because it's given in the question, we get 5.6 nanocoulombs. The next question says the diagram shows a capacitor constructed from two plates separated by glass. Firstly, calculate the area of one of the capacitor plates, state your answers in meters and then in standard form, and then the relative permittivity of glass is 3.7, calculate the capacitance of the capacitor. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, the trick you're going to have to do is to work out the area is to times the length by the breadth, but these values are given in millimeters and you've got to put them into meters. So you pop them into meters, multiply them together, and we get 1.1 times 10 to the minus 3 meters squared. Then the second one, we'll once again use our equation here. So we can see it's going to be the parallel plate capacitor's equation. So it's 3.7 times by the permittivity of free space times by the area we just worked out, divided by the separation in meters, which is 0.002, so you get 18.4 picofarads. The next question says, a 120 microfarad capacitor is charged through a 1 mega ohm resistor using a power supply with a constant output of 3.0 volts. The initial PD across the capacitor is 0. After a time equal to 1 time constant, calculate the PD across the capacitor. Then for the circuit in this previous question, calculate the PD across the capacitor at a time of 3 minutes. Then an uncharged capacitor of capacitance C is charged through a resistor of resistance R using a battery of EMF V0. Derive an equation for the time taken t for the PD across the capacitor and the resistor to be the same. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we've got to use our equation for a charging capacitor. So we say that V equals V0, which is the starting, which is the EMF, or the output of the power supply. Okay, multiplied by 1 minus e to the power minus t over RC. Now remember, RC is a time constant, so after 1 time constant, t is going to equal RC. So it's going to be RC over RC, which is going to cancel through to be 1. So therefore what we're going to get is we're going to say it's going to be 3 times by 1 minus e to the power minus 1. Pop that through and we get 1.9 volts. This next question, we can see what our time constant is because we've got R and we've got C, so we can work out the time constant to be 120 times 10 to the 6. Okay, so minus 6, my apologies, because it's microfarads times by 1 times 10 to the 6 because it's mega ohms, so we get 120 seconds. So again, we're using our equation here where we know RC to be 120, we know the time to be 180 because we don't work in minutes in physics, we work in seconds. We then pop in all the values and we get 2.3 volts. And then here we're using this equation, we can work it through here. Now it's important to note that we can say that when you work it through with the laws of logs, you'll see a half equals e to the power minus t over RC. Pop in all the values through. Now remember, to get rid of an exponential from e, we do natural log, so therefore log of a half will equal log e to the power minus t over RC, so that will cancel through. Bring that power term down to be just a normal term, so it's minus t over RC. We work it through, so t therefore equals log 2 or 0.69 RC. The next question says, a trainee electrical engineer has constructed a flat plate capacitor. The dielectric between the plates has a permittivity of 40 times 10 to the minus 12 farads per meter. The capacitor is connected to a 6 volt DC supply. Calculate the charge stored on the capacitor. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this question there's a lot of different equations we're going to have to use. Firstly, we're going to use the parallel plate equation because we're being given the relative permittivity and the separation and the areas. Remember the dimensions for the area. Now remember, they're given all in millimeters, so you have to convert them. So we use our equation C equals ER E0 over D. We work it all the way through and we get the capacitance out to be 14.4 times 10 to the minus 12 farads. We then say Q equals CV, and we want to work out the value of Q. So we pop in all the values, we know V is equal to 6, so it's 86.4 times 10 to the minus 12 coulombs. The next question says, a 220 microfarad capacitor is charged at 2.0 volts, then discharged through a 100 ohm resistor. Calculate the maximum current in the circuit and the maximum charge stored by the capacitor. Then calculate the time constants for these circuits. C equals 0.010 farads and R equals 1.0 kilo ohms. And then capacitance is equal to 4,700 microfarads and resistance is equal to 1.5 mega ohms. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, how do you work out the current? Well, again, use your equations from electricity. I is equal to V over R, so therefore it's going to be 2 over 100, so it's 2.0 times 10 to the minus 2 amps. Therefore, charge Q equals CV. Well, we know the capacitance because it's given in the question, so we're going to convert 220 microfarads to 220 times 10 to the minus 6, multiply it by our value for the potential difference there, 2, so we get 4.4 times 10 to the minus 4 coulombs. Now in this next one, what can we do? We can therefore say T equals RC. That's our equation for a time constant. So T equals RC, so it's 0.01 times by 1,000 because kilo turns into ohms by times by 10 to the 3, so it's 10 seconds. And this next one, we turn micro into farads by times 10 to the minus 6. We turn mega into just ohms by times by 10 10 to the 6, the 2 will cancel through and we'll get 7.05 times 10 to the 3 seconds. The next question says a fully charged capacitor is discharged through a resistor when the switch is closed. Firstly, calculate the time constant for the capacitor. Secondly, when the switch is closed, the capacitor begins to discharge. When t equals 0, the voltage across the capacitor is 12 volts. Calculate the voltage across the capacitor after 20 seconds. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one we know T equals RC. So we pop in all the values. You've got R from the question. Remember, kilo turns into ohms by 10 to the 3. You got given capacitance in the question. Micro turns into farads by times 10 to the minus 6. So you pop it through to get 7.26 seconds. Then in this next question we can say, right, well, V equals V0 e to the power minus T over RC. We know RC is the time constant, so it's 7.26. We know that V0 is the EMF or the power source voltage, so therefore that is going to be 12 because V0 is the maximum possible voltage the capacitor could have, so therefore that is 12. So therefore you pop in all the values. T is 20 seconds, so you get 0.763 volts. The next question says, in the 18th century, a scientist called Gordon made the first device that used electrostatic forces to produce continuous motion. A demonstration of the principle of Gordon's device is shown. A light conducting sphere of radius r is suspended from an insulating thread between two parallel metal plates. A large potential difference V is applied between the plates. There is an electrostatic force on the sphere when the sphere is charged. The capacitance C of the sphere is given by C equals 4 pi epsilon 0 r, where r is the radius of the conducting sphere. The sphere is charged by touching it onto one of the plates. The plates are a distance d apart. Calculate the electrostatic force exerted on the sphere. V equals 4,500 volts, D equals 5.0 centimeters, and R equals 3.5 centimeters as well. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this question you're going to have to use all the equations given to you. So you're given the equation for capacitance and you know that you've got R and you know 4 pi epsilon 0. So how do you work it through? So you say, right, in this first one, 4 pi epsilon 0 times by R. In this instance R is 3.5 times 10 to the minus 2 because it's centimeters into meters. So we get our answer to be 3.89 times 10 to the minus 12 farads. We can then say Q equals CV, so therefore we can work out Q. We've just worked out C. We know V is 4,500 volts, so you get 1.75 times 10 to the minus 8 coulombs. We then know from the electrical fields module that a capacitor is a uniform electrical field, so its uniform electrical field strength is V over D. Pop in those values. We know D to be 5 times 10 to the minus 2 meters, so it's 9 times 10 to the 4 volts per meter, and therefore F equals E times by Q. That is the electrostatic force equation. So you pop in those values and you get 1.58 times 10 to the minus 3 newtons. The next one says a 1000 microfarad capacitor is connected in series with a 6 volt battery, a switch, and a 22 kilo ohm resistor. Calculate the charge of the capacitor after 10 seconds and the potential difference across the capacitor after 10 seconds. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question we're looking at how much, because it's charging up because it's connected with the battery, so we're going to use the charging equation that Q equals Q0 times by 1 minus e to the minus t over RC. Now we can work out what Q0 is because it's the maximum possible charge, therefore its capacitance times by the maximum possible potential voltage or potential difference, which is that of the power source. So you can pop in those values. We've got the capacitance of the capacitor, we've got the EMF of the power source or the potential difference of the voltage, work it all through, pop in all the values, okay, in the equation. Now remember, we can work out what our time constant is because we can say time constant equals RC, and therefore we can pop in all the values, we get them through, we get 2.2 times 10 to the minus 3 coulombs. This next question we can just use the equation V equals Q over C. We've got the capacitance in the question, you've just worked out Q, so therefore you can work it all through and we get 2.2 volts. The next question says a 1000 farad capacitor is charged by connected in series with a 9 volt battery and an 18 kilo ohm resistor. Calculate firstly the maximum current, then calculate the time for the charging current to half, then calculate the time constant of the circuit, and then estimate the time for the capacitor to be fully charged. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question, it's all about thinking what information you're given. So the maximum current is going to be equal to V over R. So therefore, what is V? Well, it's the maximum current, so therefore it's the maximum potential difference, which is going to be the EMF of the power source. You divide it by the resistance of the circuit. It's 9 over 18 times 10 to the 3, because kilo turns into ohms by that method. So you get 5 times 10 to the minus 4 amps. The next one, you've got to remember the equation. The time taken to halve is going to be 0.69 times by RC. So therefore it's 0.69 times by the time constant, which is going to be R, which is 18 times 10 to the 3, times by 1000 times 10 to the minus 6. So therefore it's 12 seconds. Whilst the time constant itself is just RC, so you can work it through to be 18 seconds. Now you've also got to remember the fact that we assume a capacitor to be fully charged or discharged after 5 time constants. So you multiply your time constant by 5, so it's 90 seconds. The next question says, a 1000 microfarad capacitor is charged by connecting it in series with a 4.5 volt battery and a 47 kilo ohm resistor. Calculate firstly the maximum PD across the capacitor, then calculate the charge on the capacitor 10 seconds after the circuit is completed, and then calculate the time for the charge stored to reach 63% of its maximum value. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, the maximum PD across the capacitor is going to be the EMF of the power source, which is 4.5 volts. Now, to work out the charge on the capacitor 10 seconds after it's been completed, we've got to use our charging equation. Q equals Q0 times by 1 minus e to the power minus t over RC. Popping all the values through. Remember, Q0 is CV0, so you know V0 is the EMF, 4.5 volts. You know C is the capacitance in farads, so you convert microfarads to farads. Pop in all the values, and we get 8.6 times 10 to the minus 4 coulombs. Now, this idea of to reach 63% of its maximum charge, that's the definition of a time constant. It's the time it takes to reach 63% of its maximum charge during charging, or to 37% of its starting value during discharge. So you just work out the time constant by doing RC, so you get 47 seconds. The next question says, state what is meant by a capacitance of 37 millifarads. Then a capacitor is made up of 2 parallel plates which are separated in air by a distance d. A cell of negligible internal resistance is connected across the capacitor as shown. Switch S is closed and the capacitor becomes fully charged. While S is still closed, the plate separation is reduced to d over 2. State and explain what happens to the magnitude of the charge stored by the capacitor. Then explain how the charge is conserved when the plate separation is reduced. Then S is now open. The plate separation is increased to D. State and explain how the energy stored in the capacitor changes during this process. Then explain how energy is conserved when the plate separation is increased as described in question 1.4. So pause the video now, then unpause the video when you want to go through your answer. Right, you've got to learn what the definition of capacitance is. It's how much charge is stored per unit volt. So this would be 37 millicoulombs stored per unit volt. In this next question, we know our equation to be C equals A E0 ER over D. So therefore capacitance doubles in voltage because of the fact that the separation has been reduced to D over 2. So therefore it's an inversely proportional, so capacitance will double. We know voltage stays the same in this question, so Q equals CV. So if C is doubling, Q is doubling. Now charge will be conserved because an equal number of electrons is removed from the positive plate as is added onto the negative plate, so therefore overall the capacitor is uncharged. Now in our next question here, okay, you know that the charge will stay the same because the capacitor is isolated, so the charge can't flow. So therefore, if the capacitance halves and we use our energy stored in the capacitor equation, the energy will therefore double. And then how will this energy be conserved? Because the gain in stored energy is provided by work being done into actually pulling the plates into a further separation away from each other. The next question says, show that the capacitance of an isolated conducting sphere of radius r is given by the formula C equals 4 pi epsilon 0 r. Then figure 24.22 shows 2 identical conducting brass spheres of radius 10 centimeters mounted on insulating stands. Sphere A has a charge of plus 5.0 times 10 to the minus 8 coulombs, and sphere B is uncharged. Calculate the potential at the surface of sphere A, then calculate the energy stored on sphere A. Sphere B is brought up to to sphere A and is touched so that the charge is shared between the two spheres before being taken back to its original position. Calculate the energy stored in each sphere and then suggest why there is a change in the total energy of the system. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know the following. We know that V, okay, is going to be equal to Q over 4 pi epsilon 0 R, where V is our potential. That's an equation from the electrical fields module, which you can use because the sphere is going to produce a radial field. We then also know that Q is going to be equal to this 4 pi epsilon 0 times by V times by R. We know therefore C is Q over V. So what we can do is we can work it all through. The V's cancel through, so it's 4 pi epsilon 0 epsilon 0 times by R. To work out our potential, again, we're using that electrical potential for a radial field. V equals Q over 4 pi epsilon 0 R. So you can pop in all those values and you get 4,500 volts. Therefore, the energy stored is going to be the work done is equal to a half QV. Again, that's an equation from the electrical fields module. They're very closely linked. Pop in all the values and we get 1.1 times 10 to the minus 4 joules. In this next one, we know that the new charge on each sphere, because they've been touched, so therefore they will share that particular charge, it will equally, so it'll be 2.5 times 10 to the minus 8 coulombs. Our new potential is therefore going to be 2,250 volts because we're sharing the voltage originally, so therefore it halves. So therefore the new energy found on each of them is a half times by QV. We've got a new value of Q, we've got a new value of V, so we can work it through and we get 2.8 times 10 to the minus 5 joules. Our next question says, okay, why is there a change in the total energy of the system? Because energy will be lost or dissipated to the surroundings to heat the spheres, and that'll happen as the charge moves from one area to another area. The next question says, define the term capacitance of a capacitor. Then figure 24.23 shows a circuit which can be used to measure the capacitance of a capacitor. The reed switch vibrates backwards and forwards at a frequency of 50 Hz. Each time it makes contact with A, the capacitor is charged by the battery so that there is a PD of 12 volts across it. Each time it makes contact with B, it is fully discharged through the resistor. Calculate the charge that is stored on the capacitor when there is a PD of 12 volts across it. Then calculate the average current in the resistor, and then calculate the average power dissipated in the resistor. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, learn the definition of capacitance. It's the charge stored per unit volt across the capacitor plate, or per unit potential difference. In this next one, we use our old capacitor equation. Q equals CV. You've got a value for V, 12. You've got the capacitance, worked it through. So therefore, you can say to be 67 times 10 to the minus 6, working it through. So it's 800 microcoulombs. We then say I equals Q over T. In the question for Q, we've just worked out what previous question, we've worked out what Q is. We know the value for time given before because the time for one oscillation is 1 over the frequency, so it's 1 over 50, so you get 0.04 amps. And then we can work out the power dissipated because P equals V over I, where V is the average potential difference. So you work it through, so it's going to be half of 12 because it's the average, so therefore it's 12 times by 0.04, so it's 0.24 watts. Our next question says a 0.10 farad capacitor is used in a circuit as a backup in case of a short interruption in the mains power supply. The PD supplied to the circuit is 230 volts. How much charge can the capacitor store? Explain why a capacitor would not be a good source for powering a portable media player. Then a 12 volt potential difference is applied to a capacitor. The capacitor stores 144 microcoulombs of charge in each plate. What is the capacitance of the capacitor? So pause the video now, then unpause the video when you want to go through your answers. Right, in this first question, once again, use that capacitor equation. Q equals CV, so it's 0.1 times by 230 is 23 coulombs. Then it wouldn't be a good source because you're going to have to think about the media player would have to be very large to have enough power so it wouldn't be able to be portable, or alternatively you could say you could only power the device for a short period of time, but you've also got to remember that the capacitor loses charge and therefore loses current it can apply to the circuit over time, so you wouldn't have a constant power output. Now in this next one, you can say capacitance is equal to charge over potential difference. We know what the charge is. It's 144 times 10 to the minus 6. We divide it by the potential difference of 12 to get 12 microfarads out. The next question says, for the airspace parallel plate capacitor shown, calculate the PD when it stores 25.5 microjoules of energy. Then explain why the capacitor stores energy when a PD is applied across to the plates. And then finally, a group of scientists claim that they've developed a new dielectric that enables the above capacitor to store 1,000,000 times more charge and energy for a given PD. Explain what further steps must be taken by the scientific community and the industry before this new dielectric can be used in devices and sold to the public. So pause the video now, then unpause the video when you want to go through your answers. Right, in this first one, again, you've got to be able to work through, okay, what your value is going to be, okay, and you can work it through here. Sorry, I'll put on the wrong there, force acting per unit charge. So how you'd work it through is you would work out the value of Q by doing C. Sorry, by working out the value of C by doing C is equal to AE0 ER over D. Now remember, convert the values given from centimeters into meters or millimeters into meters. So you can work out your area by doing 8 centimeters times by 8 centimeters, but into meters, and then you can work through your capacitance overall. You can then use that to then work out what the energy is by using your equation of E equals a half CV squared. So therefore, what you can do is rearrange, make V the subject, and then you can pop in the values to work it out. Now, explain why a capacitor stores energy when the PD is applied across its plates. Well, the PD leads to a charge imbalance between the plates, so therefore there'll be electrostatic energy or electrical potential energy between those two plates. And then how can you ensure that devices must be safe and sold to the public? So you're going to repeat the experiment, do it very reliably, repeat by other research groups, other people, to make sure the results are reproducible, test for safety, test for the lifetime, look at the cost effectiveness, look at the environmental impact, and check for a big issue with capacitors, which is the idea of charge leakage, charge going between those two plates of the capacitor. The next question says, a physics student wishes to construct a capacitor that will store 31 nanocoulombs of charge when connected to an 8-volt power supply. He carries out some calculations and determines that placing 2 square aluminium plates of side length 21 centimeters at a distance of 0.10 millimeters from each other will be suitable. Determine whether this capacitor setup will store the required charge. Then state how the student could increase the charge stored without changing any of the dimensions of the capacitor or the power supply to it. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you're using a parallel plate capacitor equation. So you use that parallel plate capacitor equation, convert centimeters and millimeters into meters, and work the capacitance through. So it's 3.9 times 10 to the 9 farads. You can then say charge is equal to CV. You know what V is going to be because it's an 8-volt supply. So it's 31.2 nanocoulombs. You then write a statement concluding your findings, which is that it would store the required charge. Now in this next one, what would happen? How could you increase the charge without changing the dimensions? Well, place a dielectric between the two plates, as that will automatically increase any charge. The next question says, when a 470 microfarad capacitor is discharged through a fixed resistor R, the PD across it decreases by 80% in 45 seconds. Calculate the time constant of the capacitor resistor circuit. Then a 680 microfarad capacitor is charged fully from a 12-volt battery. At time t equals 0, the capacitor begins to discharge through a resistor. When t equals 25 seconds, the PD across the capacitor is 6 volts, so that the time constant discharge is 36 seconds. Then a capacitor of capacitance 330 microfarads is charged to a potential difference of 9 volts. It is then discharged through a resistor of resistance 470 kiloohms. Calculate the potential difference across the capacitor 60 seconds after the discharge has begun. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we're using V equals V0 e to the minus t over RC, and then we're going to work out what R is. Now, the trick is that you can see that you can link in V0 in V by saying, well, V is equal to 0.2 V0 because it's lost 80% of its charge by that point of V, so therefore it's lost 80% of its voltage, so therefore it's 0.2 V0. It's 0.2, it's 20% of its voltage of what it was at the start. pop in all the values, rearrange, make RC the subject, use your maths to convert the exponential power there into a normal term by using a natural log, so we get 28 seconds out. In this next question, very similar again, we use V equals V0 e to the minus t over RC because it's a discharging circuit. We then say V, which is the voltage at the time, is 6. The maximum voltage is 12, so you can pop all those values in. We know t equals 25, pop in the values through, work out the maths, get rid of that exponential term, and then we get RC equals 36.1 seconds. And then in this next one, what I would do for this one is V equals V0 e to the minus t over RC again, because we've got our potential difference at the start, which we know to be 9. We can pop in all the values and work it through, converting kilo and micro into those actual values, and we get our answer to be 6.11 V. Now, the next question says, a 250 microfarad capacitor is fully charged from a 6-volt battery and then discharged through a 1 kilo ohm resistor. Calculate the time taken for the charge on the capacitor to fall to 37% of its original value. Then calculate the percentage of the total charge remaining on the capacitor after the 0.7 seconds. Then the charging voltage is increased to 12 volts. Explain the effect that this has on the total charge stored in the capacitor, the capacitance of the capacitor, and the time taken to fully charge the capacitor. Then a fully charged 320 microfarad capacitor is discharged through a 1.6 kilo ohm resistor. Calculate the time taken for its voltage to drop to half of its value when it was fully charged. So pause the video now, then unpause the video when you want to go through your answer. Hopefully in that first question you've realised that the time taken to fall to 37% of its starting value is a time constant when it's discharging, so T equals RC. Remember, micro turns into farads by times 10, working it through that way, okay, times 10 to the minus 6, okay, so and kilo goes into ohms by times it by 10 to the 3, so we get 0.25 seconds. This next question, we can say Q equals Q0 e to the minus T over RC. We're working out our percentage, so we're basically going to find Q over Q0, our percentage work through. We know RC because we've just worked it through to be 0.25 seconds. We know T to be 0.7 seconds. Pop in all the values, work Q over Q0, so we get it to be 0.06, so therefore 6% of the initial charge left on here. Now you should be able to be aware that the total charge doubles because Q is directly proportional, so V is directly proportional to Q. The capacitance would not change because it's a fixed property of a capacitor. That's a very important principle. If you don't change the dimension of the capacitor, the capacitance stays fixed, and then the time taken to charge doesn't change because what does that depend upon? It depends upon the time constant, which is RC. R hasn't changed, C hasn't changed, so therefore T cannot change either. Now the time taken to fall to half of the value, we've learned this before, is 0.69 RC, so you can work it through here, pop in all the values, and you get 0.35 seconds. The next question says, in recent years supercapacitors have been developed. These components charge and discharge in a similar manner to standard capacitors but have a capacitance of more than 10,000 farads. They can be used as backup supplies in many circumstances. A 120 farad supercapacitor has an internal resistance of 30 milliohms. At time t equals 0, it stores 30 joules. Calculate the minimum time taken for the capacitor to transfer 250 joules through discharging. Suggest why this is a minimum value. So pause the video now, then unpause the video when you want to go through your answer. Right, so what you would do is you say PD across the capacitor when E equals 30 joules. Well, V is going to equal the square root of 2E over C, because we've just rearranged an equation of the energy stored in the capacitor. So rearrange that, I've made V the subject. So we can pop in all those numbers and we get out the value that for that energy is going to have 2.24 volts. So what about when it's at 50 joules? Well, we can work out V again with the same equation, but this time it's going to equal 0.91 volts. So therefore we can work out the time, okay, and therefore we can work that there through, so you can pop in all the values. So when you work it through, you know what V0 is, it's the maximum value, so it's going to be 2.24. We know what V is at that time, 0.91. We can then use the equation V equals V0 e to the minus t over RC. We're going to make T the subject. We know what RC is, okay, when we work it through, okay, so when we can work it out, we get 3.2 seconds, and this is a minimum value because this is when it has the least amount of resistance, because we're not considering any external resistance, just that input resistance there. The next question says, This question is about charging a capacitor in a circuit with two resistors in series. Firstly, show that the time constant of a circuit is about 15 seconds. Then the graph in figure 2.3 shows how the PD across the capacitor varies with time up to 5 RCs. Add a line to the graph to show how the PD across the 4.7 kilo ohm resistor varies with time. Then add another line to show how the PD across the 2 kilo ohm resistor varies with time. And then calculate the time it takes from the start of the charging for the PD across the capacitor to reach 5 volts. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, time constant equals RC. We know R is going to be the sum of the two resistors in series. We times that therefore by C. C goes from microfarads to farads by times 10 to the minus 6. So RC equals 14.7 seconds. Now you'll see that what happens for the line for the resistor, well, it's going to be exponentially decreasing because it's in series with the capacitor, so it's going to invert what the capacitor does, because as the PD in the capacitor goes up, the PD in the resistor will go down, and it's the same idea for the 2 kilo ohm resistor as well. And then remember, they'll take their potential differences in proportion to their resistances, because that is Kirchhoff's law, which will still be obeyed because this is a series circuit, so you can work it through like so. Then in terms of the time it takes for the charge to work through, well, we're going to have to use our equation that is going to be Q equals Q0 1 minus e to the minus t over RC. We then rearrange it and work it through, okay, and then you can actually, not use the Q version, not the V version of that to work it through. We know that it's going to be starting off at a value of 6, because that is the EMF supply. It goes to 5, so therefore V is equal to 5. We can rearrange it, make T the subject, work it through, and we get 27 seconds out. So thank you very much for this revision session. If we've been successful and learned in this revision session, we should be able to answer A-level physics examination style questions on capacitors, assess our understanding on the concept of capacitors for A-level physics, and then finally understand what topics you need to improve upon for A-level physics in terms of the capacitance topic. So thank you very much for taking part in this revision session on capacitance. I hope you found it very useful, and have a lovely day. Hello and welcome to this revision session on electric fields and capacitance, which is part of the AQA A-Level Physics course for paper 2. So in today's revision session, we're going to look at how to answer examination questions on the topic of electrical fields and capacitance for AQA A-Level Physics. So if we've been successful and learned in today's revision session, we should be able to answer A-Level Physics examination style questions, assess your understanding on A-Level Physics, and then finally understand what topics you need to improve upon for A-Level Physics, especially in paper 2. So how do you prepare for this revision session? Well, when completing your work in this revision session, divide your piece of paper into 2 sections. Make the section on the left hand side larger than the right hand side, and in this left hand side section, write down your work and answers to the question in the revision session. When you're doing this, make sure you write in the answers in full sentences and show your full working out. Whilst on the right hand side, write down any piece of information which you find useful, any hints and tips on answering questions from this revision session. And at the end of the revision session, write up these notes into a revision sheet for you to use independently. So how should you be revising AQA A-Level Physics? So the first step is to learn the key facts. Use the revision guides, the class workbooks, the prep notes and the textbooks to learn the key ideas of the course, and you may wish to make mind maps or write out notes yourself. The second step is to test yourself. Use Caboodle, Seneca, your knowledge checkers to quickly test your own knowledge, and you may wish to do this retrieval from your own cue cards. Then step 3, practice exam style questions. So either use the exam prep books, homework books, supervised study books, additional workbooks to answer exam questions and mark your own work, and you may wish to download your own exam past papers to do this. So your 3 steps of learn the key facts, testing yourself, and practicing examination style questions will help you in your preparation for revising AQA A-Level Physics. So what part of the specification are we covering in today's revision session? Well, we're going to be looking at 3.7.3 electrical fields, which includes ideas on Coulomb's law, electric field strength, electric potential. We're then also going to look at 3.7.4 capacitance, which covers the definition of capacitance, parallel plate capacitors, energy stored by a capacitor, and finally capacitor charge and discharge. So let's have a look now at a few multiple choice questions on electrical fields and capacitance. So the force between 2 point charges is F when they are separated by a distance r. If the separation is increased to 3r, what is the force between the charges? So pause the video now, then unpause the video when you want to go through your answer. Right, the answer here is going to be D, because we should know that the electrical force equation, Coulomb's law, is given by Q1 Q2 over K R squared, where K is the constant, 1 over 4 pi epsilon 0. So this tells us that if R is increased to 3R, well therefore F is going to become F over 9, because we're dividing by R, but because it's R squared, 3R becomes 9R squared when it works it through, so therefore it's F is F over 9 now, so our answer is D. The next question says, the diagram shows two patterns of field lines X and Y around a particle. Which row is correct when the particle is a proton? So pause the video now, then unpause the video when you want to go through your answer. Right, our answer for this one is C, because electrical field lines show the direction a positive charge would take, and gravitational field lines show the direction a point mass would take. So because gravity is always an attractive force, the field lines should be pointing inwards, because the two massive objects will be attracted to each other. But for the electrical field lines, because the direction a positive charge would take, it should be pointed away from the proton, because positively charged particles will repel a proton, so therefore they'll be pointed away from it. So therefore the electrical field is going to be X, whilst the gravitational field is going to be Y. The next question says, 2 point charges of magnitude Q are separated by a distance r. The electrostatic force experienced by each charge is F. What force will be experienced by each of the 2 point charges of magnitude 3Q separated by a distance of 2r? So pause the video now, then unpause the video when you want to go through your answer. Right, our answer here is C, because like I said before, Coulomb's law says that F equals Q1 Q2 over K R squared, where K is 1 over 4 pi epsilon 0. So if R becomes 3R and each Q becomes 3Q, well therefore we can say F is equal to 3Q times by 3Q over K over 2R all squared. So therefore 3 times by 3 is 9, 2 squared equals 4, so it's going to be 9F over 4. So our answer is C. The next question says, the diagram shows two parallel plates. They're conducting plates, and a graph of the variation of the potential between the two plates is shown. What is the magnitude of the electrical field strength between the plates? So pause the video now, then unpause the video when you want to go through your answer. Right, you should be aware that in a VR graph, okay, the gradient of the line is the electrical field strength. So when you're using our VR graph, we can work out our gradient, because it's going to be the change in y, which is 800, 0 to 800, divided by the change in x, 0 to 0.02, because we're working centimeters, remember, we work in meters, sorry, and the graph is given in centimeters. So therefore it's 800 over 0.02, which is 40,000 newtons per coulomb. The next question says, the graph shows the variation in the electrical field strength E with a distance r from the centre of a charged body. What is the potential difference between a point where r equals 20 centimetres and a point where r equals 40 centimetres? So pause the video now, then unpause the video when you want to go through your answer. Right, our answer is going to be B, because you should be aware that in an ER graph, the area under the curve is the potential difference. Now therefore we've got to work out our area from 20 centimeters to 40 centimeters. So what you can do is work out the area underneath by splitting it up into a triangle and a square and a rectangle. So therefore you can work it through by working out the area of the triangle between 20 and 40 and the square or rectangle between 20 and 40. But the trick you've got to remember is that the y-axis is kilovolts per meter, so you've got to convert those values from for example from 50 to 50,000 or from 150 to 150,000. So you work it through and you get 20,000 volts. B. The next question says, point P is a short distance from an isolated positron. What are the signs of the electrical potential and the gravitational potential at P? So pause the video now, then unpause the video when you want to go through your answer. Right, our answer is going to be B, because gravitational potential will have to be negative, because gravitational potential is always negative, because gravity is always attractive. Now, in this instance, the electrical potential will be a positive, as the electrical field is repulsive, because it's carried out in a field produced by a positive charge, and the positron is a positively charged particle, so therefore you'll get repulsion, which is indicated in potential with a positive value. So our answer is B. The next question says, a capacitor of capacitance 9 nanofarads has plates with overlapping areas of 18 centimeters squared separated by a dielectric of thickness 0.15 millimeters. What is the relative permittivity of the dielectric? So pause the video now, then unpause the video when you want to go through your answer. Right, so what you've got to do is you've firstly got to make relative permittivity the subject of the equation. Now the equation is given to you in your equation book, but it has capacitance as the subject. So you rearrange it and make relative permittivity ER the subject of your equation. So you say ER is equal to C times by D over A times by epsilon 0. Now epsilon 0 is given on the equation book, it's 8.85 times 10 to the minus 12. We know what C is, the capacitance, it's 9 times 10 to the minus 15, because we're working through as in nanofarads, and we know what the diameter is, the distance between the two objects is, it's going to be 0.15 times by 10 to the minus 3, because it says 0.15 millimeters, and we know what the area is, it's 18 times by 10 to the minus 4, because we need to be working in meters squared, and to convert from centimeters squared to meters squared is times 10 to the minus 4, because centimeters to meters is times 10 to the minus 2, and there's 2 of them, so it's 10 to the minus 2 and 10 to the minus 2, which is 10 to the minus 4. You can work that all the way through and you get your answer out to be 85, which is given to be 8.5 times 10 to the 1, which works it through to be A. The next question says, a capacitor of capacitance 10 microfarads is charged through a resistor R to a potential difference of 20 volts using the circuit shown. When the capacitor is fully charged, which of the following statements is incorrect? So pause the video now, then unpause the video when you want to go through your answer. Right, our answer here is going to be B, because if we work out the energy stored in the capacitor, we say E equals a half CV squared. So it's a half times by 10 to the minus 10 times 10 to the minus 6, because we're going from microfarads into farads, times by 20 squared, which is the potential difference. So we get 2 times 10 to the minus 3, which is 2 millijoules. So the energy stored by the capacitor in theory should be 2 millijoules. However, that's not the total energy stored, as some energy is wasted in the charging process, so therefore B is going to be incorrect. The next question says, a voltage sensor and a data logger are used to record the discharge of a 10 millifarad capacitor in series with a 500 ohm resistor from an initial PD of 6 volts. The data logger is capable of recording 1000 readings in 10 seconds. After a time equal to the time constant of the discharge circuit, which of the rows gives the PD and the number of readings made? So pause the video now, then unpause the video when you want to go through your answer. Right, our answer here is going to be D, because firstly, after one time constant, V will be at 37% of its starting value. Now its starting value is going to be its maximum, which is going to be the EMF of the source, which is 6 volts. So after one time constant, you do 0.37 times by 6, because that's 37% of 6, which is 2.2 volts. Now the time constant is equal to RC, which again is given to you on your equation book. So it's R, which is 500, times by C, which is 10 times 10 to the minus 3, because we go from millifarads into farads, so therefore it's 5 seconds. So in 5 seconds there will have been 500 readings, because there's 1000 readings in 10 seconds, so in 5 seconds there's going to be 500 readings. So our answer is D. The next question says, the diagram shows two particles at a distance d apart. One particle has a charge plus q and the other has a charge of minus 2q. The two particles exert an electrostatic force of attraction F on each other. Each particle is then given an additional plus q, a charge of plus q, and then their separation is increased to a distance of 2d. Which of the following gives the force that now acts between the two particles? So pause the video now, then unpause the video when you want to go through your answer. Right, our answer in this particular question is going to be A, because you know that F is equal to Q is say f is equal to k q1 q2 over r squared. Now again, k is just a constant, so we can just ignore them. So therefore we can say that f is equal to q1 q2 over 2r all squared. Now you might think, does the value of q not change as each one has been given a value of plus a q? Well, what's happened is we've gone from 1 being plus 1 to being plus 2 because I've added a charge, but a 1 going from minus 2 to minus 1, so actually it's still 2 times by 1, so that the value of charge at the top stays the same, but our value of r has gone up by 2, but that's been squared because it's r squared, so therefore f is now going to be f over 4. Now the thing is though, now 1 has gone from plus 1 to plus 2, and the other's gone from minus 2 to minus 1. We've still got a positive and a negative charge, so they'll still attract each other, so therefore it's an attractive force of f over 4, which is A. Let's now have a look at a few longer questions on electrical fields and capacitance. The first question says, Figure 5 shows a parallel plate capacitor connected to a 3 kilovolt DC supply. The capacitor is made from 2 identical metal plates separated by 5 millimeters of air. Each plate measures 30 centimeters in length and 20 centimeters in width. Figure 6 shows a side view of the capacitor. Draw on Figure 6 the electrical field lines between the plates, then calculate the electrical field strength between the 2 plates. So pause the video now, then unpause the video when you want to go through your answer. Well, the first one, remember what we've got to be aware of is that when we're going through this question, you've got to know that the electrical field lines will always go from your value of the highest value to the most negative value. So therefore you're going to have at least 4 straight vertical lines because it's a uniform field. Okay, and the arrows are pointing upwards. So you know this because you've got your negative value at the top and your positive value at the bottom there, so it's going to be going upwards. Now the next one, the electrical field strength, well, we know that electrical field strength by definition is V over D. That's just a fact. So therefore we've got our value of V, 3000. We've got our value of D, which is the separation, which is 5 times by 10 to the minus 3, so we work it through to be 6 times 10 to the 5. The next question says the magnitude of charge stored on each plate is Q. Show that the electrical field strength E can be expressed as E equals Q over epsilon 0 epsilon RA, where epsilon 0 is the relative permittivity, or say epsilon R is the relative permittivity of air, and A is the area of overlap of the plates. Then calculate Q when ER is equal to 1, then state the electrical properties of a dielectric material. So pause the video now, then unpause the video when you want to go through your answer. Right, how do you answer this particular question? Well, you've got to link a few equations together. The first equation is it's a parallel plate capacitor. So we can say C is equal to A times by E0 ER over D. That's an equation given to you in your equation book. But we also know that C is equal to Q over V, which is just the equation for capacitance. And then electrical field strength, E is equal to V over D. Once again, all these equations are given to you. So what you can do is therefore substitute Q over V into the top equation and therefore rearrange it and make the subject to be V over D, and then at that point substitute E in to work out your value, and therefore you can say E is equal to Q epsilon over epsilon 0 epsilon RA. The next question is legitimately just rearranging that previous equation to say Q equals E times by E0 ER times by A, then pop in all the values in. Now you're given ER in the question, you know E0 is 8.85 times 10 to the minus 12, that's given to you in your equation book, and you know your value of A from your previous question, so therefore you can say the answer is 3.2 times 10 to the minus 7. Now the last two values are just facts. It's the properties of dielectric materials, that they are firstly an insulating material, but also they will contain polar molecules or can be easily polarized. The next question says, Figure 2 shows a capacitor and a switch S connected to a parallel combination of 2 resistors R1 and R2. The initial potential difference across the capacitor is 5 volts and the initial charge in C on the capacitor is Q0. Figure 3 shows the variation of log Q over C with time after S is closed. Determine Q0. So pause the video now, then unpause the video when you want to go through your answer. Right, it's very important that you can use log graphs when trying to work out values with capacitors. Now it's important to note that you can work out Q0 from a log QT graph because we know that our y-intercept is equal to log Q0. So if you read off your graph, read off your y-intercept, and you'll see that log Q0 is equal to minus 7.4. So what you can then do is work backwards to work out Q0. So if log Q0 is equal to minus 7.4, well then Q0 is equal to e to the power of minus 7.4. So if Q0 is equal to e to the power of minus 7.4, you work it through to get 6.1 times 10 to the minus 4 coulombs. The next question says, Figure 6 shows an isolated spherical oil drop carrying a charge of plus 6.4 times 10 to the minus 19 coulombs. Assume that the oil drop behaves as a charged conducting sphere. Firstly, draw electrical field lines onto Figure 6 to show the electrical field around the oil drop. Then define absolute electrical potential at a point in an electrical field. Then an oil drop has a radius of 1.4 times 10 to the minus 6 meters. Calculate the absolute electrical potential at the surface of the oil drop. So pause the video now, then unpause the video when you want to go through your answer. Right, in this one it's very important you can show the electrical field lines around the oil drop. So because it's a spherical object, it'll produce a radial field. So you need 6 radial lines which are straight and evenly spaced out with the arrows going away from the center. Why is that? Because the arrows show the direction that a positively charged object would take in the field, and positively charged objects repel other positively charged objects, so the arrow should be pointing away from it. The next question asks you pretty much to define absolute electrical potential, and the definition is it's the work done in moving a unit charge from infinity to a place in the field. That's the definition of absolute electrical potential, which you should just learn. And then how to calculate the absolute electrical potential? Well, if you look in your equation book, you'll see that V is equal to Q over 4 pi epsilon 0 R. Now you've got the value of Q. We know it's 6.4 times 10 to the minus 19 is given in the question. We know 4 pi epsilon 0 because we can work those out from our equation book, and we've got R as it's 5.8 times 10 to the minus 5. Okay, as you can see, it's given it to you in the question. So you can work it through like that, and then you get your answer to be 4.11 times 10 to the minus 3, and then that's your absolute electrical potential. The next question says, Figure 7 shows the charged oil drop stationary in air in an electrical field between 2 parallel plates. The potential difference between the plates is going to be equal to V. So firstly, draw and label arrows on Figure 7 to represent the force acting on the oil drop. Then the potential difference between the plates is now reversed so that the oil drop is attracted towards the lower plate. Explain why the initial velocity of the oil drop is approximately 20 meters per second squared. Then describe and explain the motion of the oil drop after the potential difference between the plates is reversed. So pause the video now, then unpause the video when you want to go through your answer. Right, it's important to note that the question says to you that the oil drop is stationary. So this tells us that the forces must be in equilibrium with each other. So the idea is that when you look at this particular diagram, you're going to have weight acting downwards. So you're going to have mg acting downwards, but then in the opposite direction, you're going to have the electrical force acting upwards, Fe. Now the next question, it indicates to us why is the initial acceleration of the oil drop approximately 20 meters per second squared. Well, that's because in the previous question we said that the two forces were in equilibrium and that the electrical force counteracted the weight of our actual oil drop. Now the acceleration due to gravity, which is linked into our weight for our oil drop, is going to be about 9.81 because it's on Earth. Now that tells us that the force produced by this acceleration must be equal to the electrical force produced because it's stationary in the air. Now if you reverse the potential difference, you reverse the direction of the electrical force. So therefore we've pretty much doubled the force acting downwards on our oil drop. So now the acceleration has gone from 9.81 meters per second to be double that, which is approximately 20 meters per second squared.
Now it says then describe and explain the motion of the oil drop after the potential difference between the plates is reversed. So now there's going to be a resultant force acting downwards on the oil drop, because originally the upwards electrical force is now acting downwards. So this tells us that the oil drop will accelerate downwards, but as it accelerates downwards, because it's moving through air, the air resistance produced as the oil drop goes down will increase because it's moving faster, so air resistance gets bigger, until eventually we reach a terminal velocity between the air resistance acting against motion and the resultant force of weight and electrical force acting downwards. The next question says, Figure 6 shows two charged water droplets A and B in a thundercloud. The radius of A is 66 micrometers and the radius of B is 35 micrometers. Each droplet has a charge of minus 1.2 times 10 to the minus 12 coulombs. Assume that the charge on A and the charge on B are concentrated at their centers. The distance between the centers of A and B is 1.5 millimeters. Calculate the electrostatic force between A and B, and then the movement of air in the cloud causes A and B to move together until they touch. Calculate the work done against the electrical force in moving A and B from the position shown in figure 6 to the position where they touch. So pause the video now, then unpause the video when you want to go through your answers. Right, so how do you answer this particular question? Well, in the first one, we're trying to work out the electrostatic force. So at this point, we know that the electrostatic force from Coulomb's law is equal to Q1 Q2 over 4 pi epsilon 0 r squared. Now we've got the charge Q1, we've got the charge Q2 from our question, because it says to us that the charge of each droplet is minus 1.2 times 10 to the minus 12 coulombs. We've got our value for r squared, because you know the distance from centre to centre is going to be 1.5 millimeters, so therefore we can say that the value of r is going to be 1.5 times 10 to the minus 3 to give our value through to be 5.8 times 10 to the minus 9 newtons. Now the next one's calculating the work done against the electrostatic force in moving A and B from the position shown to a position where they touch. So the point is we're trying to work out our change in potential, so we can work out our potential energy difference. So we can say that V is equal, our potential is Q over 4 pi epsilon 0 R. So what you can do is you can work out the potential at 1.5 millimeters for one charge, so you work that through and get your value in, okay, and then at that point you can then also work out the potential at 101 times 10 to the minus 6 meters for one of the charges, so you get it to be 107 volts. So what you can then do is you've got your potential difference, so you find the difference between the two values, so 107 minus 77.2, so therefore you get 100 volts, and then you can work out the potential energy difference due to this by doing the potential difference is therefore equal to the work done over the charge, so therefore work done is the potential difference times by the charge, so it's 100 volts times by the charge of the object, which is 1.2 times 10 to the minus 12, so we get 1.2 times 10 to the minus 10. So just to clarify, why do we get the potential at 1.5 millimeters and why at 101 times 10 to the minus 6 meters? Well, if you look through here, you can see that that value is that when the difference is going to be 1.5 millimeters in that particular question, and then we're calculating the work done from that position to where they touch, so we're looking at the difference between the two of them. So when they're touching, the centers are different by about, so you can see, 66 micrometers and 35 micrometers from center to center at that point, so therefore you can work out what the distance is at that point, and that's the difference between the two of them. The next question says, figure 7 shows a simplified diagram of a thundercloud. The bottom of the thundercloud is negatively charged and the top is positively charged. Y is a point inside the thundercloud. EY is the electrical field strength at Y, so state the direction of EY, and then a charged water droplet is stationary at Y. The weight of the droplet and the force on it due to EY are equal in magnitude. The mass of the droplet is 1.38 times 10 to the minus 9 kilograms. The charge on the droplet is minus 2.1 times 10 to the minus 12 coulombs. Calculate EY. So pause the video now, then unpause the video when you want to go through your answer. Right, firstly, what's our direction of EY? Well, again, the electrical field will always point in a direction from positive to negative because it shows the direction a positive charge will move in. So therefore, it's going to be vertically downwards from the positive charge down to the negative charge at the bottom of the thundercloud, because once again, the direction of the field lines is the direction a positive charge would take. Now, to work out EY, how can we work this through? Well, it says that our water droplet is stationary, so we can say that the electrical force acting upwards is equal to the weight of the water droplet acting downwards. So we can say that our electrical force is equal to EQ, our weight is equal to mg. We're given m in the question to be 1.38 times 10 to the minus 9, so you can work out our weight to be 1.35 times 10 to the minus 8. We can make that equivalent to EQ, and therefore we can say E is going to be this 1.35 times 10 to the minus 8 over the charge of the droplet in the water cloud, and we get 6.4 times 10 to the 3 volts per meter. The next question says, the base of the thundercloud and the ground beneath it can be modelled as two plates of a parallel plate capacitor with air between them as shown. The base of the cloud is circular with a diameter of 2.75 kilometers. The base of the cloud is 340 meters above the ground. Show that the capacitance of the capacitor is about 1.5 times 10 to the minus 7 farads, and that the capacitor discharges when the lightning strikes the ground. The charge stored in the capacitor before it discharges is 87 coulombs. Calculate the energy available for the lightning strikes. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we're going to have to use our equation for parallel plate capacitors, which is C is equal to A times by E0 times by ER over D. Now, you're given the value of D from the question is 340 meters, the distance between the two plates. Now, you've been given our diameter for the cloud to be 2.75 kilometers. So therefore, because it's a circle, you can therefore work out the area by halving your diameter to get your radius, but always work in meters, so convert your kilometers into meters, and therefore you can work out your area to be pi r squared, and you get 5.9 times 10 to the 6 meters squared. You've got your value of E0 and you've got your value of ER from the questions. Okay, so what you can therefore do is pop them in to get 1.55 times 10 to the minus 7 farads. Remember, E0 is going to be 8.85 times 10 to the minus 12, and ER is going to be the relative permittivity of air, which is going to be 1. Now, the next question asks you to work out the energy. Now, you've got charge, and you've got the idea of your you've got your charge there, and you've got your capacitance as well. So you can use your equation E is equal to a half Q squared over C. Now you can pop in your values. You've got your charge from the question. You've just worked out capacitance, so you can work out your energy to be 2.4 times 10 to the 10 joules. Look to see what values you've been given in the question and refer to your equations, which are given to you in your equation book. The next question says, figure 6 shows a circuit used to transfer energy to a lamp in a camera flash. A battery of EMF 12 volts and negligible internal resistance charges the capacitor when the switch is in a position S1. The capacitor discharges through the lamp when the switch is in position S2. Assume that the capacitor is discharged completely after each use. The capacitor has a capacitance of 0.85 millifarads, so that the energy stored in the capacitor when it's fully charged is approximately 0.06 joules. The lamp emits a flash of visible light when the voltage across it is greater than the minimum voltage V min. The duration of the flash is 55 milliseconds. Assume that the resistance of the lamp is constant and has a value of 31 ohms. Calculate V min. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, you're working out energy, but you've been given capacitance in the question, and you know what V is. It's 12 from the information given in the question. So we say E equals a half CV squared, so you get 6.1 times 10 to the minus 2. Remember to convert millifarads into farads by times and by 10 to the minus 3. Now, in this next question, you're trying to work out V min. Now, it's the idea of a capacitor, which is going to be discharging. So we can say that V is equal to V0 e to the minus t over RC. So what you can do is you've got all your values through because you know what V0 is. It's going to be 12 there. So you know what R is. You got C in the question because you're given the value of R and you're given the value of C from your previous one. And then you know we can work it all through and you get 1.5 volts.
Now the next question says, the charging circuit includes a resistor and a 12-volt battery. The battery transfers a total energy of 50 milliwatt hours during its lifetime. Explain why only half of this energy can be transferred to the capacitor, and then calculate the maximum number of times the battery can charge the capacitor during the battery's lifetime. So pause the video now, then unpause the video when you want to go through your answer. Right, so the idea is that the energy is dissipated in the resistor in the charging circuit. So what you can therefore say is E is equal to a half CV squared, and so therefore what you can therefore do is then if you can work out the energy that's dissipated as it goes into the circuit and then how much is dissipated in the resistor, and you'll see that half of the energy is dissipated in the resistor as it's charging up. Now the next one is calculate the number of times the battery can charge the capacitor during the battery's lifetime. So the first thing you've got to do is you've been given an energy but you've not been given it in joules. So you're going to have to convert 50 milliwatts hours into joules. So you do that correctly, you get about 180 joules. Now to convert from milliwatt, so if you think about the unit is that energy is power times by time. Well, your power is being given in milliwatts and your time is being given in hours. Now joules is going to be when your power is given in watts and your time is given in seconds. So to convert from milliwatt hours into joules, you multiply by 10 to the minus 3 to turn milliwatts into watts, and then you will also multiply by 3600 to convert your hours into seconds. So therefore that works out to be 180 joules. Now remember, it's half of that because half of it you've said has been dissipated out of the circuit when it's charging up, so you've only actually got 90 joules. And then we know that each charging process is going to be, discharging process is 0.06 joules from the previous question, so we get about 1500. The next question says, the capacitor is then replaced with one of much greater capacitance. Explain how the replacement capacitor affects the duration and brightness of each flash. Then explain how the replacement capacitor affects the number of flashes the battery can deliver, assuming that the capacitor discharges completely each time the flash is used. So pause the video now, then unpause the video when you want to go through your answer. Right, so the idea is how will the replacement capacitor affect the duration and brightness of each flash? Well, the idea is you've got a much greater capacitance, so therefore you've got a greater duration, or the brightness will decrease more gradually because you've got a greater time constant, so therefore it'll take a longer time to charge and also a longer time to discharge as well. So whilst the initial brightness is going to be the same, it's going to be brighter for longer, because whilst your initial value of charge you're going to have in your capacitor is the same, okay, the time it takes to discharge is going to be longer, so therefore it'll be brighter for longer. The next question says, explain how it will affect the number of flashes the battery can deliver. Well, there's going to be fewer flashes to be delivered because the energy stored in the capacitor is greater, because you know E is equal to a half CV squared, so we know that C has increased, therefore E has increased, so therefore it'll take, the fewer flashes will be delivered each time, so therefore the energy stored is greater, so therefore be fewer of them delivered each one. The next question says, define the electrical field strength at a point in an electrical field. And then figure 2 shows a point charge of plus 46 microcoulombs placed 120 millimeters from a point charge Q. Position P is on the line joining the charge at a distance 66 millimeters from charge Q. The resulting electrical field strength at position P is 0. Calculate charge Q. So pause the video now, then unpause the video when you want to go through your answer. Right, the first one is just the definition of electrical field strength. So the definition is, it is the force per unit charge on a positive charge in the field. So the electrical field strength is the force per unit charge on a positive unit charge. Now, how do you work out the charge, calculate the charge here? Well, you'll notice that there are two charges. There's Q, and then there's the second one, which is going to be 46 microcoulombs, and you'll notice that at the resultant at P is going to be 0, so we can equate the electrical field strength from the left hand side and equal to the right hand side and work out your value. So what you can say is, you can say 46 times 10 to the minus 6 over 4 pi epsilon 0 0.054 squared, which is the distance from that charge on the right hand side to P, is equal to Q over 4 pi epsilon 0 0.066 squared, because again that's the distance from the charge on the left hand side
to P. You can then rearrange it all, make Q the subject, and you get Q to be 6.9 times 10 to the minus 5, or 68.7 microcoulombs. And that also makes sense because you'll notice that the two are going to cancel out, and you notice that the 46 microcoulomb charge is actually going to be slightly closer. So therefore that tells us that the charge on Q is going to be slightly bigger to negate the fact it's slightly further away, to give equal electrical field strengths, so they cancel each other out at P. The next question says, a small rubber ball coated with a conductant paint carries a positive charge. The ball is suspended in equilibrium from a vertical wall by an uncharged non-conducting thread of negligible mass. The wall is positively charged and produces a horizontal uniform electrical field perpendicular to the wall along the whole of its length. Figure 3 shows that the thread makes an angle of 30 degrees to the wall. The thread breaks. Explain the motion of the ball. So pause the video now, then unpause the video when you want to go through your answer. Right, so what's going to happen is that you'll notice that when the thread breaks, there's going to be two forces acting on the ball, because you've got a charged ball, okay, and it indicates it's got a positive charge, so it's going to follow the electrical field lines in the horizontal, so the ball is going to accelerate horizontally to the right hand side, but because it's now falling, it will accelerate vertically downwards due to the force of weight. So therefore we've got our electrical force accelerating to the right, and our weight force accelerating it vertically downwards. So therefore you're going to have acceleration in a straight line at 30 degrees to the vertical away from the wall, because you're going to have two accelerations act on the object, one in the horizontal due to the electrical field, and one in the vertical due to the gravitational field. Right, so I hope you've enjoyed this particular revision session where we've looked at answering A-Level Physics examination style questions on electrical fields and capacitors. So hopefully you feel you can answer those A-Level Physics examination style questions. You can assess your understanding on A-Level Physics, and finally understand what topics you need to improve upon for this particular topic. So thank you very much for watching this revision session on electrical fields and capacitance for AQA A-Level Physics on a paper 2 topic. Thank you very much for watching, and have a lovely day.